All right, I'm going to do a little lesson on how to write net ionic equations. So the first thing you do is you start with a reaction, and then from this reaction you look at, there's a lot of what are called spectators, or things that aren't actually reacting or changing in this equation, and we want to focus on what is actually going through the reaction. So that's what is in the net ionic equation. So we start with just a regular reaction, and here you can see we have a neutralization reaction where you have a strong acid and a strong base giving you a salt and water. And that's typical when you have strong acid, strong base, always gives you some sort of salt and water. Now here, watch your ratios, because here I have 1 sodium going to 1 hydroxide, whereas here I need 2 sodiums to balance out the sulfate. That's because sulfate's a -2 charge, so I need 2 of them to balance it. So if you have to create this side of the equation, watch your charges, make sure you balance them, do your crisscross, that sort of thing. Okay, so the first thing we're going to do when we make an ionic equation is we are going to split apart all of the ionic compounds that when they get into water, they would dissolve into their separate ions. So we're going to say we have 2 hydrogens and a sulfate ion. And that's what the sulfuric acid, when it's in water, would split into. The sodium hydroxide right here would split apart as well, and I'd have 2 sodium ions and 2 hydroxide ions. Now on the other side of the equation, we are going to split this one apart because it's aqueous, but liquid water is going to stay together. It doesn't become ions. So when the sodium dissolves, the sodium sulfate, we have 2 sodium ions floating around in solution, and we have a sulfate ion floating around in solution. And then we have our 2 waters. Okay, so there is one extra step, and that extra step happens to be when you look at these guys. So what you've started to learn is that these don't actually exist, because when they're in water, what they do is they link up with the water and they become a hydronium ion. So this right here, whenever you see this, it's basically the same thing as this. And so that's a more accurate representation, is to talk about hydronium ions. These 2 things are used interchangeably. So what we need to do is we need to correct for that, because aqueous hydrogen ions don't actually exist. So I'm going to go back through, now that I've written my whole ionic equation, and I'm going to take anywhere where I see hydrogen ions, I'm going to turn them into hydronium ions. So here I have 2 hydrogen ions, so I'm going to change them into 2 hydronium ions. The problem is now my equation is not balanced, because since for every, what I did is I turned these into those, and in order to do that I had to add 2 waters. 2 waters. So I just added 2 waters to this side of the equation, which means I need to add 2 more waters to this side of the equation. So I'm going to take my 2 and I'm going to turn it into a 4. And so now I have an ionic equation. That's the hardest part of this whole type of problem, is making the ionic equations. So now what I have to do is I have to cross out anything that exists on both sides of the equation that remained unchanged. So for instance, I don't have any hydronium ions on the other side of the equation, and so that stays. But I do have an aqueous sulfate ion here and here. So that cancels out because it didn't change. It's the exact same on both sides. It is called a spectator ion. The other thing that didn't change is I have 2 sodium ions that are aqueous on this side of the equation and this side. By the way, these have to be the same. If I take, these have to be the same. If I took solid sodium and I turned them into aqueous sodium ions, that's a chemical reaction. But they were 2 sodium ions floating around in solution on this side, and there are 2 sodium ions floating around on that side. So now I have my net ionic equation. My net ionic equation says that I have 2 hydronium ions plus 2 hydroxide ions, and that's turning into 4 waters. So really what you have, and that shows you this when you write out this whole thing, is that this powerful neutralization reaction of a strong acid and a strong base is water forming. Because really this is the active part of the acid, and this is the active part of the base. And when you put those together, you get water. And so that is the net ionic equation for this neutralization reaction. So this right here is your net ionic equation. We're going to try a different one for a different type of neutralization reaction. So let's take this one right here. Oh, you know what? I don't think I can slide it that much further. I thought I was so prepared. All right. So if you have a metal, so we'll take solid magnesium, and you have an acid. We'll take hydrochloric this time. When you take a metal and an acid, this is also a neutralization reaction, and what you get is you get a salt, and in this case it's going to be MgCl, and I'm going to need 2Cl. And it's aqueous. I need 2 of them. Remember, when I do this, I've got to get my magnesium, which is a 2+ ion, to pair equally with chloride, which is a 1+. So since this is a 1+ and this is a 2+ ion, I need 2 of them. All right, and then I also need, it creates a salt and it creates hydrogen gas. All right, and then to get this to balance, I'm going to stick 2 right there. All right, so here's my equation, and then I'm going to write my net ionic equation, and I'm only going to break apart things that are aqueous, which means in my net ionic, my magnesium stays the same, but I have 2 hydrogens that break apart, and I have 2 chloride ions. Those are both aqueous. And then on the other side, the things that break apart is just really, the only thing is this one. I do not break apart covalently bound diatomic gaseous hydrogen. That stays together. The only things you break apart are ionic compounds that are aqueous. Leave everything else alone. So I've got magnesium ion, and I do not have Cl2 here. I have 2 chloride ions. I'm going to just fix that. Okay, and then I leave my hydrogen gas the same. You know what, actually I'm going to need a little bit more space, so I'm going to squish that in. Okay, so I need 2 hydrogen gas. Why do I need to squish it in? Because remember, I have to take these and I have to convert them into H3O, because hydrogen ions in aqueous solution do not exist. Now, I don't recommend notice that I didn't change it right when I wrote it. Because what I worry about is whenever you change the hydrogens, remember, if I have 2 hydrogens, I'm going to need 2 waters to turn it into 2 H3Os. I worry that if I just do this straight up, I'm going to forget that I add these in, and I'm going to forget to add them to the other side. So my strategy is write the whole ionic equation, and then afterwards go through and change these to H3O. Because then it's on my mind that in order to change my hydrogens into hydroniums, I added 2 waters, which means I have to add 2 waters to this side of the equation. All right, so there's my ionic equation, and now I can go through and I can cross things out. And the first thing people would probably do is go, oh, magnesium, cross that out, cross that out. No, this is solid magnesium, like those strips you guys love to get your hands on in the lab that light up when you put them on a Bunsen burner. And these are magnesium ions floating around in water. These 2 things are very different from each other. You cannot cross them out. And so I also don't see any hydronium ions on this side. You can't try and force it and make it cancel. These hydronium ions do not exist on the other side. The only spectator ion I see on each side are these 2 chloride ions. So in this case, when I go to write the net ionic equation for this, it's a little messier looking. It's not a nice water forming reaction. I've got magnesium solid, I've got 2 hydroniums, I've got 2 chloride ions, and then I've also got on the other side magnesium ions now. I've got hydrogen gas, because that doesn't cancel with hydrogen ions in any way. And I also have 2 waters. This is a net ionic equation. It makes people very uncomfortable that it didn't form some nice, neat, and tidy water-forming reaction like you see up there. But it is still a net ionic equation, and this is the answer. So what you have to keep in mind is, when you have a strong acid and a strong base like you have up here, you will get a water-forming reaction like this. But when you have other types of neutralization reactions, like here where you have a metal and you have an acid, you can get something pretty messy, and that's okay. Don't try and force canceling things. The only types of things that cancel are things that did not change from one side to the other. The magnesium that was solid, neutral element turned into a charged ion floating in solution. These are not the same thing, so you don't cancel them. These are, so you do cancel them. Also, on the same note, you can't take and go, oh, well, I'm not going to turn this into hydronium. I'm just going to keep it as like 2 hydrogen ions, and so that I can cancel these. Those aren't the same either. Those are not the same. So these are ions floating around in solution, and that is hydrogen gas. Very different. Okay, so we've got to leave this as is, and that's it. So this is how you do ionic equations. You're going to have some practice on this, and they become really important when we get to redox at the end of the semester. So they don't go away. You've seen a little glimpse of them when we talked about double displacement reactions last semester. They're back. They're back to stay. You're going to see them again in a future unit. So make sure you understand them. Maybe watch this again if you need to, and do some of the practice problems.